All right, welcome to Let's Get to the Marks. Going through a titration practical question today for A-level chemistry, suitable for all exam boards. This particular question is an AQA one. Let's go. This question is about an experiment to determine the solubility of strontium hydroxide in water at 20 degrees. Strontium hydroxide is slightly soluble in water. Strontium hydroxide solution reacts in a similar way to calcium hydroxide solution. Some solid strontium hydroxide is added to approximately 1 decimeter of distilled water in a stoppered flask. The mixture is kept at 20 degrees. Every day, the mixture is checked. If no solid is present in the flask, more strontium hydroxide is added, remembering it's sparingly soluble. So we're checking to see if it's become fully saturated. On the day when no more solid needs to be added, the flask is opened and the mixture is filtered into another flask and stoppered. So we got the filtrate from that and stoppered. A 25 centimeter cube sample of the filtrate is transferred to a conical flask, right? With a pipette and a few drops of indicator is added. The sample is titrated with 0.1 mole per decimeter hydrochloric acid. The titration is repeated several times with further samples of filtrate. The results are shown in table 1 on page 8. We'll get to that in a minute. Suggests why the solution is kept until no more solid needs to be added. We want to create a saturated solution. So to ensure the solution is saturated. Now, why are we doing that? We want to work out the solubility of strontium hydroxide. So we're trying to work out grams, how many grams will dissolve in a set volume of water. So we need to ensure the solution is saturated. Right, suggests why it is important to remove the undissolved strontium hydroxide before the titration. So if you think about it, what we've got going on, we've got water with strontium hydroxide in there, right? Group 2 element, isn't it? So I'm going to need two OHs with it. So I've got my strontium hydroxide in there. It's aqueous, it's dissolved in water. And what's eventually going to happen is I'm going to end up with some strontium hydroxide that has not dissolved in water. All the water has become saturated. And so we've been told here that it's only slightly soluble in water. So I've got some solid strontium hydroxide hanging about in here. Now, if I then want to use a titration in an effort to work out how much strontium hydroxide has dissolved in the water, the problem is the hydrochloric acid will also react with the solid strontium hydroxide. So when I work out how many moles I've used of hydrochloric acid, it won't really tell me how much strontium hydroxide was dissolved in the water. So we need to remove the undissolved strontium hydroxide so it cannot react with the hydrochloric acid. So because the strontium, oh my days, hydroxide solid would react with the HCl, and that is acid. So we don't want the strontium hydroxide solid to react with the acid and make us not be able to work out how much strontium hydroxide has dissolved in the water. So those are your marks for the first two. Let's zing down. I'm sure we will need to come back up in a second to read that method. So 2.3, after the filtration, the solution is stored in a stoppered flask, suggests a reason for stoppering the flask. So think about it, right? We're trying to find out how much strontium hydroxide will dissolve in a set amount of water. So we're going to put it in like a stoppered flask, i.e. we want to put a stopper in there. And we've got our strontium hydroxide solution sloshing about in here. So there's several reasons. Remember later on, we take 25 centimeter cubed of that out. So we're going to use that. We want to make sure, there's a couple of reasons you could put here. We want to make sure the strontium hydroxide is evenly dispersed throughout the solution. So we could say that to make, so we can invert it. Remember, when you add to volumetric flasks, you often stopper it and then you invert them, which means turn them upside down a few times to ensure even mixing or distribution of the contents. So we can invert flask to ensure equal distribution of strontium hydroxide in the solution. So we basically want the strontium hydroxide molecules to be evenly dispersed. So if we try and work out how many moles, it's as accurate as possible. Another reason is to prevent evaporation of water. So yes, some of the water will always exist in a gaseous form when you have a bit of space in the flask, but it won't be able to escape. So once the atmosphere is fully saturated with moisture, no more evaporation will take place, no net evaporation. So to prevent evaporation of water, why is that important? As this will affect any calculations, basically. It's going to increase the concentration. If water evaporates and we think we've got 100 centimeter cubed in there and we've only got 90, it's going to increase the concentration of the strontium hydroxide. Okay, so these are some examples of answers you could put here. Either one of those would be good. All right, let's zing down to 2.4. 2.4, the diagrams in figure 2 show part of a pipette with a graduated line. So graduated line we got here. Which diagram identifies the pipette that is correctly filled? So here's our graduated measurement line, which when you're drawing solution or a liquid into a pipette, where should the meniscus sit? Now, the meniscus is the bottom of the curve here. Where should it sit? Well, you need it in a reliable place where you can get it every single time the same. Obviously, to get the corners of the meniscus, the edges of the liquid there and there is pretty difficult. And then to get that halfway is even more difficult. But if you say, I just want the bottom of the meniscus to sit on the graduated line, you can repeat that time and time again. This is the repeatable one. And so this is the correct answer. You want the meniscus to sit on the graduation line. Okay. Next question. 2.5, solubility can be quoted as grams of solute per 100 centimeter cubed of solution. Table 1 shows the results of the titration between strontium hydroxide and hydrochloric acid. These can be used to determine the solubility of strontium hydroxide. So we're going to do a little titration here, and that is going to help us determine the solubility of strontium hydroxide. So our table has final burette reading. We over here, 1, 2, and 3. They did 3 repeats and a rough titration. And then we got the initial burette reading of the rough and of the 3 repeats. And then we've got the titra, which is the volume of the hydrochloric acid that had to be added to the strontium hydroxide in the flask to neutralize it. And we've got that here. It says, give the equation for the reaction between strontium hydroxide and hydrochloric acid. Now, you would assume we've got a 6 marker here that's going to be one of the marks. Calculate the mean titra using the data in this table. That's going to be another mark. And then use the mean titra to calculate the solubility of strontium hydroxide in grams per 100 centimeter cubed of solution at 20 degrees. And I would assume that is going to be the next 4 marks. So we've got 6 marks laid out here. The equation for strontium hydroxide and hydrochloric acid, hey, that is just going to be the equation you get with a group 2 metal generally. And it said it reacts exactly the same as calcium hydroxide. So we're going to look like this. Group 2 metal hydroxide. We're going to add that to hydrochloric acid. Of course, we've got base and acid. This is like a neutralization reaction. So we're going to end up with strontium chloride. It's a +2 ion because it's from group 2. And so it's going to join with 2 of those chloride ions. And then we're going to get water, aren't we, left over? And let's just see, is that all bibbly-babbly balanced? No, it's not. So we need to balance this up. Well, I've got to double this over here, evidently. And now I've got 1, 2. I'm going to need double bubble on that as well. And that is balanced. Lovely jubbly. 1 strontium, 1 strontium, 2 chlorines, 2 chlorines, 2 hydrogens there, 2 there. That's 2 times 2 is 4, 1 oxygen there. And I've got, 2 oxygens there, and I've got 2 there. Yeah, all balanced. Beautiful. So there's your first mark for writing out that equation. Now, the second mark, calculate the mean titra. Now, here's where they're testing you on your knowledge of analyzing data tables. So you need to know that the rough titration is just used to speed up the process. So you can get quicker to the end point when you carry out your repeats. So we don't use that in any calculations. So we don't need the final or initial burette readings. I mean, there could be mistakes there you want to check, but I think they'd hint at that in the question. So we're just going to look at the titras. And we need concordant results. Concordant results, depending on your exam board, results that are really close to each other. So within 0.1, some exam boards 0.2, whatever. But here we go. There's only 2 concordant results here, 32.45 and 32.40. 33 is not concordant. It's too far away from these to be considered accurate. So we're going to use these concordant results. and we're going to calculate the mean titer. So we're going to do 32.45 plus 32.40, and then we're going to divide that by 2. And there's two possible answers here. Me, myself, I like to go 32.425, but as it's a 5, you could alternatively round this up to 32.43. And so you'll see both of these appear on the mark scheme. They're saying, look, we generally work in 3 significant figures or 2 decimal places. So they're saying round that stuff to 2 decimal places, please. 32.43, because 425 rounds up to 43. Okay, enough of my waffle. Let's get on with the bulk calculation that's going on here. So what do we want to do? I don't want to skip up. But if I skip back to this, I'm going to go back to the stem. Yeah, let's go back to the stem of the question. So if I zing up here, there's some data that we need in order to calculate this. So let's get back up to the stem here and have a look, because we need to do a titration kind of calculation here. So we've got 0.1 mole per decimeters of hydrochloric acid. We need to remember that, okay, guys? And we need to remember that 25 centimeter cubed was used in the conical flask. So we've got 25 centimeter cubed of the strontium hydroxide, and it's been titrated with 0.1 hydrochloric acid. Let's go back down to our level calculation, and let's see if I can hey, got all my data back. That's what I'm looking for. Okay, so we've got so just to give you the info, and then you should pause the video and have a go at the calculation. We're using this concentration of acid, 0.1. That is the most crusty concentration unit ever, 0.1 mole per decimeter HCl. What has the titration told us? It's told us the volume we used. So immediately you should be thinking to yourself, geez, I've been given concentration and volume N over C times V. So we want to do concentration is 0.1. So I want to go 0.1 times the volume. That's the concentration, by the way, times the volume, which I'm going to use 32.425. Of course, that's in centimeter cubed. We need it in decimeters. So let's divide by 1,000. You should know that by now. You need that in decimeters. And that's going to give me my moles of hydrochloric acid. So we're going to go 0.1 times 0.03245, and that is going to give us 3.245 times 10 to the minus 3. So I've now worked out my moles of hydrochloric acid. Notice I use N for moles, number of moles, because M is often for mass. So I've got my moles of hydrochloric acid. We've now got to find out how much strontium hydroxide. Remember, that hydrochloric acid neutralized this strontium hydroxide. Now there's a ratio of 2 to 1. So I needed double the amount of hydrochloric acid to neutralize the amount of strontium hydroxide dissolved in the solution. We got rid of the solid excess, so we're just left with the stuff in the solution. So we're going to find out the moles of strontium hydroxide. I need to divide this by 2 because the ratio is 2 to 1. So let's divide it by 2, and that is going to give me 1.6225 times 10 to the minus 3. So I like to label these things on my working out. Obviously, you can smash this all in your calculator, and but as you go, I would recommend labeling it so you don't get lost. So that is the strontium hydroxide moles, and I would assume we get one of our 4 marks for the calculation for that. So we've already gone. We've got 1 for working out the moles of hydrochloric acid, 1 for recognizing the ratio, working out the moles of strontium hydroxide. We now know the moles of strontium hydroxide in our solution. We used 25 centimeters. Do you remember there was a point in the method which said 25 centimeters? They want grams per 100 centimeters. So we're going to work out grams per 25. Now I've got the moles. We need to turn that into grams. How are we going to do that? And then I need to turn this 25 centimeters into 100. Right. So I'm going to need this bada bada bing, bada bada bong. So a lot of people might have got to this point and then they might get lost here. We've got the moles of strontium hydroxide. We need to turn it into the mass in grams. And so we're going to go 1.6225 times 10 to the minus 3 times the MR of strontium hydroxide. Well, strontium, I believe, oh my gosh, is it 87.6 or 86.7? One of the two. I'm going to get this wrong probably. 87.6. And then OH is 17. But remember, we got 2 of them. because we got OH to the 2. So 16 for the oxygen, 1 for the hydrogen. So I've got 34. I'm going to have to do that in the old calc. So let's go and multiply that by 87.6 plus 34. And that equals 0.197. So I have 0.1978 grams per 25 centimeters. So here's the extra tricky little mark. We needed to do the MR and work out the mass. That is our third mark. The fourth mark is for realizing that they want it per 100 and we only titrated 25. So we need to times by 4 to get up to 100. And then we can find how many grams per 100 centimeters. So times 4 equals 0.78. Oh my God, that 7 is disgustingly. 789184 grams per 100 centimeters, right? So per 100 centimeter cubed, whatever. Sorry, yeah, whatever. Don't know what I'm doing here. Right, I need to round that, don't I? I can't really write that 0.789184. So we can do that as 0.79. So yeah, or 0.7892, whatever we want to round that to. But that is, I don't know if it said, did it say 2dp or anything? No, I'd probably go with you just round that up to 0.79 maybe. Yeah, let's just go 2 decimal places, 0.79, and that is grams per 100 centimeter cubed. Beautiful. There we go. And that's the fourth mark. Lovely bubbly. Right. Lovely jubbly. Okay, 6 marks. So we worked out the mean titra and that, and there we go. We worked that out. Bing, bang, bong. That's the end.
You're still here? It's over.